And hello from the campus of Carnegie Mellon University in Pittsburgh, Pennsylvania. We welcome you to today's SEI webcast using LLMs to evaluate code. My name is Shane McGraw, the outreach team lead here at the Software Engineering Institute, and I'd like to thank you for attending. We want to make our webcast today as interactive as possible, so you can add your questions and comments in the YouTube chat area now, and we'll get to as many as we can. We also got a number of questions prior to the webcast, and we will work in some of those as well. Now I'd like to introduce our featured speaker for today. Dr. Mark Sherman is the Technical Director of the Cybersecurity Foundations Directorate within our CERT division here at the SEI. Mark leads a diverse team of researchers and engineers on projects that focus on foundational research on the lifecycle for building secure software, data-driven analysis of cybersecurity, cybersecurity of quantum computers, cybersecurity for and enabled by machine learning applications, and detecting fake media. Welcome, Mark. Thanks for joining me today.
Oh, thank you, Shane, very much. We started doing this kind of work because the use of generative AI or open models, large language models, the various names of these, generated a lot of interest about the kinds of things they can do, and some of them seem quite remarkable. And since we're in the software business, it was a natural question of, well, can this be used either generate or evaluate code? And so what I'm going to be sharing today are some of the results that we got as we try to explore that topic.
Great.
I just want to mention that this has been an ongoing project. There's been a team of people who've been working on this, and I want to acknowledge all the various folks that have been helping us with all the technical and other kinds of statistical analysis that I'm going to be sharing with you today. So I'll just give a very brief background about generative AI. At this point, I think lots of people are familiar with some of the key concepts, and share with you some of the expectations, and I'd be curious to hear if the audience has those same expectations, and then what the actual evaluations have been as people try to look at this technology, and then our own experiments to see whether it validated that or contradicted that, and then try to help position what we've learned as to what might be useful for people in practice. So, very beginning, autocomplete is very familiar to everyone. Everyone who has a cell phone uses text messaging. They're very familiar. They start typing, and it comes up with suggestions to come next. That is a relatively simple model of how you can predict the next things to do with a limited amount of data. What has happened with the generative AI revolution, if I can say that, is that instead of having a cell phone amount of power behind you, you have whole data centers. And people are probably aware, they've read in the press, that these things are huge. They take many, many computers. They intake enormous amounts of power. They're restarting 3 Mile Island nuclear power plant just to feed one of these kinds of data centers. But when you start doing that, you get pretty remarkable kinds of results. Now, in the code world, these kinds of ideas have been going on for quite a while as well. So this actually is from a presentation about 6 years ago, in where we talked about autocomplete, just like we had for the cell phones, but now it's for programming. It says, in this case, it's a for loop, and it says, what kind of things would you like in the for loop? Programmers who are familiar with this know that usually if you're doing a for loop, you're iterating over some structure, and so it has suggestions of how to index various kinds of structures. Now, if you look a little carefully, even though this is 6 years ago, it has the same technology that we've been talking about now. That people know about ChatGPT, they may not recognize what the GPT stands for. Well, as generative pre-trained transformer, that was there 6 years ago already in practice in coding in order to just do things like the completion. But now we take that same data center concept and where we have huge amounts of processing, rather than figuring out the next line of code based on a couple of lines of code, we're talking about what might be entire programs. And so you can start to question things like this, and this is sort of one of the sort of toy experiments that we ran. Just write a Pascal program to do something, and rather than having a particular line come out, a whole collection of code comes out. And at first glance, this looks pretty interesting. You generated a whole program, so it looks like there's something there that might be worth exploring. So what does it happen? So that's sort of our anecdotal view. If you look at places like Silicon Valley, you have people like Mark Zuckerberg saying that this stuff is so good, it's going to replace all of his mid-level engineers. You have other folks saying that they're not going to hire any more software engineers because they don't need them. The AI is going to do the work. Well, that's an interesting kind of comment, Mind you, these are folks who are also trying to sell you access to their systems that do these kinds of things. What's a little more either interesting or scary, depending on one's point of view, is you have corporate CEOs making the same kind of thing. So here we have the head of BP Oil saying, I'm going to need 70% less people doing programming. The computer will do it, and we'll just use them to kind of check the computer code afterwards. Or even at Google, and we'll talk a little bit about Google later, they said a quarter of all the new code is being generated by AI, and then just programmers will look at it later. So we've got people who are telling Wall Street, that's the scary part, because Wall Street actually holds you to these things. It affects your stock price, it affects their options, it affects their pay, that they're going to be using AI to generate all of this code. When you start taking a little more care at evaluating what this is, you see some initial academic studies that have come out. So these are studies that are from Stanford, they're from NYU, they're from Columbia, over in Europe, they're from UCL, University College London, in where they tried to use these systems to either generate or check code. But I found out, like in that top left one is from Stanford, it says people who actually had the ability to use AI in writing wrote less secure code. When they looked at Copilot, one of the more common things, by the way, when we say Copilot here, we almost always mean GitHub Copilot. For those who are familiar with the various ways that Microsoft is using the name Copilot, we're really talking about specifically the one that's used for generating code. But 40% of those came out to be vulnerable. Half the problems that had problems with them, they could only fix with this kind of technology. So as we looked at a more careful, systematic study, there seemed to be lots of problems. But a lot of these are maybe not necessarily representative. Just for example, for the Stanford study, they wrote some simple web applications because in some of their experiments they were dealing with just for initial students. The ones with University College London, those were looking at what I call computer science problems. For example, they were trying to generate and fix programs that look for the greatest common denominator. Common divisor, sorry. So, that's not exactly what people are really trying to do when they're trying to use code. So we're questioning, can we do something a little more systematic that actually might provide some insight as to what people are actually doing? So we decided to use something called the Secure Coding Standards. Quick plug, if you're interested, you can use that URL and get your own copy of it. But it's the collection of our research in how people program. So not exaggerating, we have examined over 100 million lines of source code looking for weaknesses, vulnerabilities, other problems with that. Over the years, and we're talking about well over a decade here, that we've been doing this, we have found certain patterns of places that people make mistakes that generate insecure code. And so we have, based on our experience, examples of bad code, and as you'll see in a moment, examples of good code. So to be a little more concrete, here is a standard page from the standard. I don't really expect people to read this. Every now and then I'll put up some code. If I actually want you to look at the code, I'll sort of blow it up so that it's visible. But the point here is just to look at the overall picture. What you see is in red is a bunch of code that actually has a vulnerability in it. That's what that represents. And again, it's typically what we found when we were examining code. On the bottom, what you see is the correct way that should have been programmed. So we have an example of the wrong way to do it and the right way to do it. Now, in this particular case, I tell people they don't have to look at the code. I've done this enough times that people will always try to stare at the code anyway, so I'm not going to give you eye strain. I'll just point out in this particular example, the problem is that it's got a formatting string that's not done the right way. So when it's not done the right way, it introduces vulnerability. When it is done the right way, you wind up avoiding that vulnerability. So what was our experiment? Our experiment was, how is the state of the practice of these machines, of these LLMs? Is it getting better? And we had this compendium of data that we could use. So we decided to ask ChatGPT, and in general, I'll say ChatGPT rather than constantly qualifying it with all the different language models, to identify either the presence or the absence of errors in, again, we have approximately 1,200 examples of this code that I've talked about in C, and C++, and Java. So we can give it the bad code, see if it finds the problem, and we can give it the good code and see if it recognizes there are no problems. And so what we did was we looked at ChatGPT 3.5. This was earlier on, a couple of years ago. And some of the results we got some feedback when we presented those results of, well, the systems are getting better. maybe you should try those experiments again with the newer systems. So we then tried it again with ChatGPT 4 and GitHub Copilot. And then 4.0 came out, so we tried it again with 4.0. And altogether, we did about 2,700 runs of various things that we tried. Good code, bad code, different languages, and so on. Now, we know that these systems tend to learn from experience. If you try to do something and then can do it again, it picks things up. So we didn't systematically repeat any trial. We did repeat some of them, and we'll talk a little bit about some of those examples. Interesting, as far as an experimental design goes, everything that I've shown, all the examples I've shown, along with their solutions, so all of that bad code and all the correct code was available on the web. We've published these standards for years. And so to the extent that OpenAI's description of how they train these systems is true, these models have actually seen everything that we're going to test already. They have seen all the bad code, they've seen all the good code. And in fact, some of the examples even mark the bad code as saying, here is where a problem is. So at least in principle, all of these models have seen all of these examples already. There's a whole other line of research, which we're not going to talk about here in any detail, in where they try to avoid those particular issues. And there's a whole new set of example programs that some researchers are using, which have been deliberately kept off the web. The source code has been kept out of the literature and so on, so that people have the ability to try these things without worrying about whether they've been polluted somehow in any of the kinds of training materials. But this stuff was all out in the open. But finally, as we'll see later, sometimes it's hard to tell whether these systems got the right answer or not. And so, as I mentioned at the very beginning, we also had various SMEs, subject matter experts, on the various languages and programming, take a look at those results and then see whether that actually had a reasonable answer or not. So that's kind of where we set it up, how we thought about things and why we tried to do it. I'm curious if we've gotten anything from people back yet on just the general idea of trying to go after understanding better.
No, nothing
Okay.
introductory here more.
Okay,
Yeah.
that's fine. So we take a look at some of the examples of how this stuff came out. So the first was, can you find an error and can you fix it? And so we took the same problem that I showed earlier, because it's a simple enough problem to show on a chart. And in all cases, in 3.5, in 4.0, and Copilot, it got the right answer. And it simply said, yes, as we mentioned, the problem was the string formatting was wrong. It says in the first one, it's wrong. Second one's wrong. Third one is wrong. A difference that you'll see is that in the first one, in 3.5, the earlier model, it simply said, I see a problem. What you see in the later ones is not only do I see a problem, but you see an actual fix to the problem as well. So it went beyond simply acknowledging that there was some kind of problem. And in general, this again is the larger description that came out of 3.5. And again, it's a description of the problem. When you look at the next systems, like 4.0 and Copilot, it gives you a much more detailed explanation of the problem, as well as giving you the actual fix to the problems. So in the later models, we're getting a lot more information back from them, as well as proactively ways to address things that came out of those analyses. So that seems to be generally true. So again, looking at just the collection of output that we got from these different models, we see that 3.5 had about 400 or so pages of output, whereas you see something like ChatGPT 4 had going close to 700 pages. And so these were a lot more verbose, a lot more detailed, a lot more coming back at you, as one of the things that we saw as the different models started to elaborate. However, in one case, we showed you an example where everyone got it right. Oh, I should be careful. I said everyone. I know that sounds anthropomorphic. I am under no illusions. These are not people. So just to be very clear here. So in some case, all of the systems got it wrong, even the later systems. And so again, the details of what this rule are not important. What was pointing out is that all of them said there's nothing wrong with this code. It looks like an appropriate use, seems to be correct code. So sometimes, even with the later models, all of them missed the mistake. Sometimes you got some improvements. And before we saw there's much more discussion and elaboration. Here we have an example where the earlier ones said this does not look like a problem, does not have any obvious errors. When we get to the later versions of the models, it says, oh, yes, there is an error. This happens to be an uninitialized memory. I think that's probably common enough that I don't need to explain it much. But both For and Copilot said, you have something that's not initialized. There is a real problem here. So you do see some improvements in the code. Now, there are sort of well-known issues one has in general with large language models, these generative AI systems. One of them is memorization, where basically you put in code and it comes back with the same code. So here's an example of a program that was correct. The error that this is trying to correct, and I'm not showing the erroneous version of it, but it has to do with SQL injection, and this is a way to avoid SQL injection. What you see here is that it's not complaining about the SQL injection saying yes or no, but it says it's found some other problem that the password that's used in order to do the analysis. And again, I'm not going to delve into the details of the code, but it says you should be doing this kind of processing on the password. And then when it comes up with what it calls the fixed correct answer, you see that it's the same code that came out. And in fact, as we highlighted, the problem that is complaining about, that is the hashing of the password, was done correctly in the original to begin with. So all it did was reflect back and then come up with some error which really wasn't there. By the way, we also did this with the later systems. This time, it didn't improve at all. 4.0 complained about the same kind of error. Now, this was one that we found kind of interesting in trying to understand how the systems were analyzing the code and the kinds of behaviors that one might see. Again, I'm not going to ask people to try to read the code on the left. That's not the intention, but I'll summarize it as saying it's trying to have two different processes or threads, and I know the difference, but I'm making it simple here, update a database at the same time. And it's a well understood, people teach about this all the time in concurrent programming. There's certain ways you do that in order to prevent deadlocks. Otherwise, you can wind up freezing a system because you're trying to change things at the same time that you can. And so when we do this and we gave it to 3.5, it said, this looks like you've got a race condition. And then explains a little bit more what a race condition is. Now, this is different than some of the other things we looked at. The other things we looked at were usually very local, almost syntactic. And therefore, it wouldn't be surprising that you could do a sophisticated pattern match and discover the problem that you saw in some of these other examples. Here, at least to my mind, there needs to be a deeper understanding analysis of how the program is behaving to know that when you've got these different locks that are being claimed, that they're not being claimed in the right way, and therefore you have a deadlock situation being set up. I thought that was quite remarkable. In trying to understand whether this was really remarkable or serendipitous, this one we did try a couple of times. We gave it the correct program and said, tell us what you think. Is this program okay? And it says it's got the same problem. Well, what might be going on? Our speculation is that there's a lot of literature out there about using mutexes, about using locks, and that there's a danger if you're not careful about causing these kinds of locked up situations, deadlocks. And so what we're seeing is a sophisticated pattern match. It saw a bunch of code. It saw that there were locks in there, mutexes in there, and it said, then I must be having some kind of issue with deadlocks because I've read 1,000 pages of computerized textbooks that say when I have mutexes, it's all about preventing deadlocks. And so it asserted there was a deadlock here.
A couple clarification questions, Mark.
Sure.
I've been real quick. Santiago asked to confirm the judgment of right/wrong response is provided by a human.
Yep.
You went through over 2,600 responses.
Yes. Or whatever that final number was, we did a 9-mumming exercise among all of us. But yes.
And then Ohad just asked if you use Claude rather than ChatGPT for any of this.
So what I'm going to be talking about are basically 3 different ones, 3.5, 4, and 4.0, well, Copilot. We have, I'll use the word played around with a variety of other ones, Gemini, Claude, other systems as well. Nothing as systematic as this. Similarly, I'm talking about C and C++ and Java here. We've also tried Python and other languages. Again, nothing as systematic that we can really share. That's just something to learn from.
Right.
I mean, we can share what we did, but I don't think there's enough data there to draw any kind of conclusions.
Okay, great. Thank you.
Sure. we tried the incorrect program again. Remember, I mentioned that we weren't going to try this again. We didn't want it to learn. Well, in this case, we did try it a second time. And all of a sudden, the issue with the locks disappeared. And so, again, if it's just doing a pattern match, well, it's pattern matching on a variety of things. And this time I decided not to raise that one as an important issue. We tried it again, and it's still not finding the problem with the race condition. So how come one time it did, one time it didn't? Again, we're speculating that we're looking at is some sort of sophisticated pattern matching that's going on here. When we try the correct program another time, but now this is later, so these systems and models have advanced, it now has correctly understood it, and it specifies why it thinks the correct program is okay. Again, it correctly orders the locking. That's sort of the generic answer, how one does this. It really was able to identify why the correct code worked the way it's supposed to work. If we just sort of round it out with the other experiments, we tried it with multiple of these large language models. And again, as we saw before, it not only came up with the discussion in the later models, it came up with the actual code that you're supposed to use in order to fix things. And again, it came out with the correct way to do it. It is done slightly different ways, but they both accomplish the same kind of need. They're supposed to avoid the deadlock. Now, sometimes it can be a little tricky to evaluate this. Going back to the comment of, did a human look at this? Here's an example where we had a human have to look at this. So I'm not going to spend a lot of time on the C code. I'll expand a little bit just so people are aware. What we have is a structure, and sometimes in languages they're called records. They're called a variety of things, but a composite type. And if you're building embedded systems, which a lot of weapons systems that we look at do, you want to make sure you can do that as fast as possible. And so if you want to compare two structures, it's tempting to just compare the bit patterns in the memory. They found out one, found the other. If all the bits match, it's fine. They don't match, you say it's not right. Well, it turns out that's not really the right way to do it. You'll get the wrong answer because of things like how compilers compact structures, or they insert padding in structures, or what have you. So you wind up comparing pieces of data, bits, that have nothing to do with the structure whatsoever. This is artifacts of the way that the compilation system has built it. And so the correct way to do it, which is shown on the right here, is you actually have to take the structure apart and piece by piece. So again, this is somewhat made up. There's a left and a right, and then an array. And so you have to compare each of them individually. Now, the array is a sequence of bits. And so it does make sense then to use that particular comparison in order to make that. So here's an example in where we have a programmer could look at this and say, I did it this way. They see the one on the right and they say, I get it. I understand. Somewhere in some lecture, I was told about how compilers work. And yep, I appreciate this is what I've got to do to make it correct.
Eric asked real quickly, did you try different prompt engineering techniques to run the tests?
So in the examples I'm giving here, we did not. We deliberately kept the same one. Depending on time, and I think we're going to have time, we'll talk a little bit more about some of the prompting that one can use and some of the experiments that have been run and what the results of those experiments are.
Great.
But yes, context we'll learn is going to be very important. But for this one, we try to keep it simple and consistent. And that, well, again, we'll see more about that later. So as I mentioned, inside the structure of this particular example is a string of bytes. And there's a certain way to compare a string of bytes. And that's the way to do it. When we asked these large language models to examine the problem, they came up with the real problem. You're comparing two instances of a structure with the wrong way to do it. And again, if you're not familiar with C, it doesn't matter other than to know that using that particular comparison call is not the way to do it. It got it right. However, it didn't get right how you compare the individual pieces inside the structure. So it got the compare the left, compare the right, and then it did something different when comparing that array of character array, the bytes that I had. It didn't do a memory compare, which is the right thing to do here. Instead, it assumed that there was a string there and used a string comparison. And that gives you a different answer in C than the memory comparison that we offered before. So it made a very subtle change. If you're a programmer who's just looking at this and says, oh, I see the problem, the system helped me, that I didn't unpack the structure before I compared it. I'm going to copy and paste this code, you would have wound up making the wrong answer. Now, there are some people who are experts in C, just to take a small digression here, would say, well, maybe that was a string. It's not usually the way it was. So can you really fault the system? And our reasoning here was that, yes, you could fault the system. And the reason is that it has examined lots of code. And there's a whole variety of research in reverse engineering, actually, in where taking binaries apart and objects apart and reconstructing what the code looks like to figure out what the identifiers might be. And if you have something that's, pointers to whatever, you'll see things that look like next and first and so on. If you have structures that have strings in them, you see things like name or dress, city, or what have you, things that are string-like things. If you just see a network protocol kinds of things, you see array of buffers, you see a character, you see an array of bytes like we see here. Looking above, when we saw the initial code was just random bytes, it wasn't set up a string. The name of the structure element wasn't name or street or city or what have you. Then seasoned programmers would look at that and say, I know this is not a string. This is just an array of bytes. And so again, based on reverse engineering AI that's been done for quite a while, it should have recognized that this was not a string, but an array of bytes. And so we said the system, got some of it right, but didn't get all of it right. And based on what we believe these systems should be able to do, it should have gotten it right. So perhaps the good news, which I'm not going to elaborate here, this was 3.5. Turns out that the later versions actually did make that fix correctly and did not assume that it was a string, also correctly interpreted that it was an array of bytes. But this is an area where you actually had to have someone who's really knowledgeable look at that in order to understand. Can you trust a programmer to actually catch that? Well, that's something that we're going to take a look at in a bit. Now, here's another violation that we found. Again, I'm not going to go into the details of how C works other than to say, this is the way that the command injection vulnerability gets introduced into a system. Now, for those who are not familiar with command injection as the name of a vulnerability, a very common form that people will probably recognize is SQL injection. And so this is the way that you can accidentally introduce command or SQL injection. And the short answer is, and you probably can't read the little tiny code at the top, but the way to deal with this is just don't do this, right? Don't provide the capability by which you can go in and just start executing any kind of code that you want. Now, interesting, when we gave this a 3.5, it said, well, what we think the issue is, what the system thinks the issue is that you're using this wrong print statement somewhere up above. And you should use the function snprintf in order to do whatever kind of analysis is there. So first, it's missing the really big problem, right? SQL injection is a top 10 error where you really want to find it. But on top of that, it identified a problem that wasn't there. The original, remember this is the pink version, already was using that particular call. So it made up an error that wasn't there and then told you to go correct it. So this is bad, right? 3.5 really didn't get it. The good news is that when we went to the next generation on 4, you see, danger, Will Robinson. This is security vulnerability. It's command injection. It's incredibly critical. Don't do this. Don't do this. And again, it's got much longer explanation. I only, took out sort of the juicy parts to show here. But we found something interesting as well with the next version when we went to Copilot. It turns out that there are some times when you can't get the system to actually give you an answer. And we tried this several times and it came back and say, I'm not going to tell you if there's something wrong here or not. Being the kind of people we are, we of course just pushed and prodded the system to your point about prompts and prompt engineering and so on. And eventually we got it to spit out a different answer. And the answer was, here's how you use this vulnerability to delete all the files on a computer. I'm not going to reproduce that piece of the answer. So what have we seen so far in these kinds of experiments? Well, sometimes it gets it right. Sometimes it gets it wrong. We do see improvement, but to a point, we'll talk about that in a moment. We do see memorization, and unfortunately memorization of both correct and the incorrect code. We believe there's inconsistent pattern matching going on. We see subtle mistakes in the fixes, so although it claims to make a fix, it may not be a correct fix. Obviously, it's inventing non-existent problems and enjoys problematic guardrails. Now, as I mentioned, and I think we have in the next slide, we see improvement as these systems evolve. So 3.5 was of one generation, and the what I call 4, which was GitHub 4, Copilot 4.0, was another generation. And what you can see is that pretty much in all the different classes, whether we're talking about C or C++ or Java, and whether we're talking about identifying vulnerabilities in bad code or recognizing the lack of vulnerabilities in good code, it improved. So you saw in the worst case before, only got the answer 40% right. Near the end, it's getting 80% right. And again, the different languages have different models. The question now becomes, well, is this line going to continue? And there's a line of discussion going on in the research community questioning whether you'll see this trend continue or not. And the reason is that there's two reasons. The first is you get improvement by having more data that you use to train the system. Well, at this point, pretty much all public code that's out there has already been given to these systems. There's not another 100 petabytes of C code out there to train these systems on. So while it improved in going from 3.5 to 4, there's not that same quantum amount of information to start training it on to go from 4 to whatever comes after 4. Similarly, what you see in some of these things is a bigger model. Well, we've gotten to the point, as I mentioned, not tongue-in-cheek, that you need a whole nuclear site to power these things. So the expectation that you're going to have, again, another quantum leap, these are like 3 orders of magnitude in the number of parameters that you're going to have in these systems is not likely. And so expecting to extend these lines, we don't think is a very reasonable kind of thing. Now, we also did learn what other piece of interesting information. It's not on this chart, so I'll just explain it. If you remember the heritage of these, 3.5, if you like, was sort of the initial public version. Obviously, OpenAI had stuff before 3.5, and you saw me mention 2 very early on in the presentation. And what you saw was sort of a divergence. In one path, they made a much bigger model. That's what 4 was, that's what 4.0 was. And by bigger, I mean like 3 orders of magnitude bigger, much, much bigger. GitHub Copilot took a different path. It didn't make a bigger model, but it added all the additional training specifically on code. And so it was a very specialized version of the large language model. If you go to talks, you read papers, and they say, how do you make these systems work better? They say, train them on the domain that you want to use it on. It turns out, then again, I didn't include the data here, but we have it in other papers, that the bigger model improved more than the data-specific model. And further, it regressed less. That sometimes these models that used to perform at one level got some things wrong in the next version. It introduced fewer mistakes than the code-specific one. And so that goes against conventional wisdom of, well, if I had trained it more on programming code, it would do better, as opposed to having basically a bigger hammer. Bigger hammer did better than a specialized hammer. Now, that's an interesting idea. It's a question of whether how that can be applied in an engineering context. I mean, it's very easy to wave one's hands and say, well, gee, just always use the bigger model. Well, the bigger model costs a lot more to train, costs a lot more to use, and is not necessarily specific to some of the other things that might be included in there later. And so one probably is facing an engineering choice of whether it's better to do the specialized training that's more economical, I have the engineering trade-off, or again, to use, as I said, the bigger hammer. But the fact that they were different in this way when all the conventional wisdom is do the specialized training to get better performance, and this result suggested just the opposite.
So quick question here, more just
Sure.
from another listener. Have you experimented with building a low rank adaptation to specialize the general LLM, ChatGPT, or Copilot to find specific language, code, vulnerabilities, and reduce costs?
So the best we have is what I just shared, which was we looked at the at the specially trained model that OpenAI did. That's what the GitHub Copilot is. So we ourselves did not try to train a new model. But in all these cases, the systems make mistakes. And so again, the conventional wisdom in AI in general, not just with this code model, is AI, you use it to ask a question, and then you need to have a human look at the answer and see whether it's reasonable or not. Are these lead pipes in a house? Is this the right bail amount to be set, and so on? There's all sorts of AI systems, all sorts of studies that show that you need the human in order to try to correct what's going on here. Well, in the case of programming, it says that people don't seem to have the judgment in order to do that. This is sort of like PricewaterhouseCoopers, and where they had people going out in their engagements and they just could not catch it. Again, from Facebook, one of the engineers, that they make mistakes, and we've seen them already here in this talk. And it takes a really experienced developer to spot the issues. And I gave you one subtle example in where you might not expect a programmer to get it right. The challenge is that programmers believe the AI systems over their own trust of their own expertise. So that first quote came actually from that same Stanford study I mentioned earlier, where they had students and sometimes they had some professional developers build some of these things and use AI systems. They would get feedback from their evaluation saying this is insecure code. And when given a choice, the programmers would prefer what the AI system generated over what they believed to be secure code, even though it was the wrong answer. Now, in this particular study, they had one additional result, which, again, many people found interesting. I have not seen it replicated, but it's interesting enough to share. Turns out that the more experienced the developer, the more they were willing to defer to the AI system. You might have expected the experienced developer to say, well, I'm really on top of this. Seems it's just the opposite. They're so interested in doing things as quickly as possible, and that's speculation on our part, that they actually accepted the AI's results faster than the inexperienced ones. Where the inexperienced people didn't trust at all what was going on, so they spent more time to try to figure it out. But this is not a unique result. We found again in more surveys that respondents found that when the security issues came with AI, but they still believed the AI system was more secure than what they were doing. So you can't seem to rely on the people to actually go ahead and do this on their own. There's an additional study, again, we're not going to go into detail on that one here, in where they try to give programmers code to review and say, is this right or is this wrong, and so on. What they found that after about 9 times of asking this, there was such fatigue in the programmers, they just basically couldn't do it anymore. And so the comments like you saw early on, and where the AI is going to generate 70% of the code, and then 30% of the time, the programmers are going to look at this. That's just not apparently how people are able to operate, to look at large amounts of code and constantly try to figure out whether it's right or it's wrong. So spend some time on how do we manage this situation. So we've seen that there's some good here, there's some not so good here. We want to take advantage of as much as we can. And before we get into some details here, I'm curious if there's anything more that's come up.
No, but we had one, like I said before, tons of came in prior to the webcast. So we could just work in one of those.
Sure.
Frank had asked, how does the effectiveness of LLM reviews vary with the kind of programming languages used?
So the things that we saw and the data that I saw actually did not distinguish among programming languages. There was a lot of data that talked about general purpose AI systems versus those trained specifically on code. But I haven't seen any data that says these systems are better, say, at C or Perl or or Ada or what have you. There might be out there, but I just haven't seen any of those particular kinds of results come through yet.
And then one just from Lamont, again, might be off the wall, but they came in various times. Are there particular types of software, language, or deployment scenario that are better suited for machine learning-based software assessments?
Sure. So again, now we're into the well, I'll give you 2 answers. The first general answer is, and this is more anecdotal, and I've heard this from many researchers, and sort of we believe it as well. The more common it is that you want to, the more common problem you want, the more likely this is to give you what you want. And that's just a realization that these systems are trained on code that's out there. If you're going to try to invent something new that no one's ever seen before, it's never seen it before either. Right. And so the likelihood that it will generate it well goes down dramatically. If you're asking it to do a bubble sort or something. Again, there are textbooks written about this, and it's seen all 100 or 100,000 of them, as the case may be, and therefore it can probably come up with something that's straightforward. Something that's a page or less of code seems to be the sweet spot that people seem to anecdotally aim towards when they're trying to do something like that. But it's something that is a common kind of thing that you might do. It's sort of it's a time saver more than really an intellectual advancement here.
Great. We can work in a couple later.
Sure,
Yeah.
sure. So what do we mean by context? Well, we talked a little bit about this with prompt engineering. Just something simple. We'll start simple. We talked about that code from University College London. They tried 40 problems. These are the computer science problems. On its own, it fixed half of them. If it started to kind of prod it in the right direction, not necessarily give it the answer, it got better. So for example, what was one of the prompts that they gave it? It was in this mathematical problem they were trying to solve. They actually said, here's an example of something that's wrong. So, you produce this answer, that produced the wrong answer, go fix it. When it gave that level of hint, it was now able to get up to 75% of the fixes done in this particular study. Now, this was a far more extensive study, and I think more interesting to the questions that people were asking about earlier, and where they had two studies, and they ran some programs and come up with some errors, and then they tried different levels of prompting to see if it could find the answer. And I need to, truth in advertising, both of these studies have exquisite detail about what the prompting was and lots of variations. I purposely abstracted out what their answers were, what their conclusions were, so that you could see in the aggregate what kinds of results they got. But if you want to look at the details, there's staggering amount of details in both of these studies. So in the first one, they gave it a variety of programs, and they did 4 different or 5 different levels of prompt, depending whether you consider no prompt a level or not. If they did nothing, they said basically just fix this. Between 20 and 30% of the time it got fixed. And they had different languages and different systems, and that's why there's sort of a range there. If they said to the program, fix CWE, whatever the number is. For those who are not familiar, there's a coding system for common weaknesses. In fact, that's what CW stands for, common weakness enumeration, in where there's one that says if an uninitialized variable, a buffer overflow, and so on. And in many of the tools that generate program analysis will say, on line 13, you've got CWE, 13 as the error. So it said, okay, I'm going to tell these programs that, you should go generate a fix for this particular CWE. And it tells it the CWE. I mean, it has another static analyzer that said, no problem, 13 is in this. So it said, go fix CWE 13. At that level, it got between 29 and 40% of them right. The next thing was, at the next level, it didn't simply say fix, CWE 19 or 13. It said, it gave you the whole diagnostic that came out of, Fortify or SonarQube or whatever is being used here. And when it gave that additional context, it got up between 45 and 60% of the time. It then added additional context, and this is sort of programmer-generated context to the error of, fix the uninitialized variable within this particular program because of CWE 13, what have you. It managed to get between 72 and 90% of the time. So when you start giving it more context, it was able to get better and better results out of the system. There's some anecdotal studies as well. Well, I mean, they're not measured as well, but people saying when I tried this, it worked a lot. Then you start feeding it things like what libraries are being used and what languages you're interfaced with and so on, that it starts to get these much better kinds of proportions. At some point, you wonder whether you're just giving it the answer, which is sort of interesting for that last part. When you actually describe the repair task, initialize I on line 14, very directive. For some reason, it did worse. So in that case, it only got like 45 to 50% of the time it got fixed. I don't have an explanation for that. The authors in this study didn't have any explanation for that either. We both just recognized that that was what the data showed. So that was one interesting study about this. Now, they did another study. This one I could not abstract as easily, in where they gave no prompt. And this collection of programs, they managed to find 76% of the errors. The other time, they gave very, very extensive and, to my mind, complicated hints to the system I wanted to do, what the prompts would look like. And I could only really call it extensive prompts because these are like almost paragraph long prompts of take a look at this and think about that and consider that, and maybe you should think of this. And it wasn't the same. The first one, at least, things like generate fix for CWE, that's a simple one and frankly a repeatable one, right? Everyone who's listening to the call does these kinds of things, knows what a CWE is, and if they wanted to try it, they could do it on their own. With their extensive prompts, it required an awful lot of information about what the program was doing, how the program was doing it, and feeding that in. So it may have been much better results. 97% of the time it worked, but I didn't see any systematic way that you could explain to people as to how you would generate those prompts. So with enough context, it can get a lot better. And we see some results about what kinds of context seem to help.
One comment from
Sure.
George here, in case you could reply, if you have a reply to it.
Mhm.
The more interesting solution I would seek is how to check the correctness of code again against the intended behavior. Seeking consistency is useful, but more important is what the system does. Any comment?
Sure. Well, so we have a straight man.
Yeah.
Thank you very much. So part of the issue here, and what you've just seen are sort of refinements of the concern of, well, I'll call it the concern, but the need to have the human in the loop. And whether the human is generating prompts or has to look at the code and make it a value judgment as to the correct code or not. There's fatigue, there's lack of experience, and so on. Are there ways you can approach to minimize the human in the loop? And so I could talk about two of them. One of them is a research one, one's one that was actually done in practice. So this is the research one. And the idea here is that you take a program, I'll just say a function to make it simple. You run it through your favorite static analyzer, run it through Covariety. It comes out with an error. Say, you take that error, you take the code, you give it to your favorite large language model and say, what do you think? Is this a problem or is this not a problem? And you go further and say, if it is a problem, generate the example that shows the problem. If it's not a problem, generate the formal proof that it's not the problem. And one of the advantages of these kinds of systems is that they're able to actually spit out this information. And the idea is, if you have a problem that it says it has a fix for, or that it claims it has a fix for, you can take the original problem, you can take the program, you can take that fix, and then you feed that into a theorem prover, rather than having the human look at that and say, yeah, I see that's the problem, I see that's the fix. You take that automation and you move it into another piece of automation. And when that automation says, yes, I believe my theorem prover, I believe enough that it's not buggy, then I know that I've got a good fix. And I know that without the human having to intervene. So this is sort of, I said, the leading edge research going on here.
Right.
Some of the tools vendors are taking sort of an intermediate step. And this is what so I've talked with product managers of these companies, and they're saying this is more in their research departments. They don't know that it's actually come out in their product yet. But since they said it in an open forum, I'm willing to share it here.
Yeah.
And where they sort of use an iterative process. So they take the code, they run it through the large language model, and it says, here's the fix. They take the fixed code, so to speak, they run it through their analyzer again. If it comes out clean, they say, it got it fixed. If it comes out with another error, feeds it back to the large language model, fixes that. Again, just keep repeating that cycle until you get clean code. Is it the correct code to the point, is it do what you want to do or not? They don't really say a whole lot about that, but it's a way that they can automate and get the human sort of reduced in the loop as to how that can work. So this is a very research way. The other one was sort of a very practical way. There's another one that came out of industry that I thought was really interesting. This was done at Amazon. I have not seen another example of this. And so I don't know whether this was a one of lucky or whether this was really a wave of the future. And it goes to some of the things that people were asking out before. They had a specific task. They had a variety of Java 8 and 11 programs, and they wanted to upgrade them to Java 17. So it was a really well-defined task. And the way they approached it was they trained it a large language model. The material I read didn't say which one, so I can't share that. I just don't know. But they trained it specifically on Java 8, 11, and 17, how to do those fixes. Now, they also had the specific case in where the programs that were going to be changed were written to Amazon coding standards. So rather than being arbitrary code that's out there in the field, it was written to corporate standards as to how things are structured and laid out and names and so on. So it was very repeatable kinds of code that they could be looking at. In addition, there's something called open rewrite, which if people are not familiar, but there are ways that are, in fact, they call them recipes as to how those kinds of things should be done by humans. But they also fed that into the training of the large language model, saying, if you're going to do this kind of task, here is the way that the thing should be rewritten. And perhaps most importantly, given this discussion, they had unit tests for all of these old programs. And so they ran it through the systems, this newly trained system. It generated the new code. They ran the new code against the unit tests. So we know what the behavior that was supposed to have, because by definition, unit tests are supposed to be checking that. And if it passed, then they had a successful translation. And they said the overwhelming the time it passed, and the few times it didn't, programmer got involved and they were able to go fix it. And they claimed they saved over 4,500 developer years. I actually might believe that in this particular case. Just to go quickly, some other things, I want to revisit some stuff. So we saw some code being generated and sort of hand our way of saying, gee, this is really helpful. Well, here's that original Pascal program that we had before. And it looks like, okay, it generated a lot of code, that's kind of helpful. But if you look a little more carefully, inside the middle of that program, it says, out of that boilerplate, by the way, here's where you actually have to do the hard work. It didn't come up with the hard work. And so if all you need is sort of boilerplate around something, well, okay, that's something that a large language model will help with. Now, it's a bit distressing because it says you need to implement the actual algorithm. Guess what? This algorithm has been out for close to 1,000 years. And it's not only has been out for 1,000 years, it's been published. It was published, originally actually in Hebrew, because it was a Jewish calendar, Hebrew calendar to begin with, lunar calendar, but it was also published by people like Gauss, who is very well known, and translations of all these. I mean, this is sort of well-documented thing. So if it's searching the whole web, it's got lots of things here. But instead, what you saw was something like this, and where here's the boilerplate, by the way, you go figure out what has to go there in the middle. So to your point of, imaginative things, it probably can't help with imaginative things. All the superstructure, it can probably help with. Now, another place that we found that it was useful, and this was kind of a surprise to me, says, I mentioned we tried different languages and so on. So we tried this with Python. I'm a Python programmer, probably many people are. And I did not know that basically there's a function in Python that does this. And so because it could basically understood, it had read in all of the Python library and documentation, the answer it gave me was, just make this call. And again, so this is now a time saver. This is a case where I did not know some particular function. I could ask it to help me with a particular function, and it identified something that I didn't know. So again, we see a place where it could help. It's not writing the program entirely, but it is helping me be more productive. So what does this mean in practice? Well, I started off by saying Mark Zuckerberg is saying he's going to get rid of all his mid-level engineers. Well, he learns just like all of us learn. And instead of thinking that AI is going to do it all for him, he realizes that AI is going to improve the productivity of his programmers. And so now, instead of saying, I'm not going to hire any more level programmers, he's saying, when I hire programmers, I'm going to see if they can actually use AI as a productivity improvement. And we've had people from Google come here and explain some of the things they're doing. And what we see a lot is that people are using this code completion that we mentioned before, looking up legacy libraries, understanding documentation, generating documentation and test cases. These are things that accelerate conventional programming behaviors and knowledge, rather than trying to remove the creative process of the programming. And the people who have come to us informally have saying they're getting 20, 30% increase in productivity. Talking to programmers here at the SEI who have used some of these kinds of things, anecdotally, they say, yeah, that feels about right, that I am using this stuff this way. It's filling in some blanks for me. It's giving me some boilerplate, whatever, and it does make me more productive. And so those are examples where this technology does seem to be bearing some fruit. So from my perspective, the overwhelming claim, this stuff is going to solve the world. Well, it doesn't solve the world, but it does do a lot of things, and one shouldn't throw out the whole technology just because it can't do the universal answer. So what do I recommend you take away from the discussion that we've had today? Yeah. Don't get rid of the practices that you're doing now to build secure and scalable software. Those still exist. Those still should be used. You should educate management as necessary on what the stuff really can do. We saw all the hype in the beginning. Lots of managers read that stuff in the trade press, and you get, one of my mind's kind of extreme statements like, from the person from British Petroleum saying, well, I'm going to get rid of most of my programmers. And, that's not really what you get. But there's a lot of low-hanging fruit there. We talked about completion and documentation, survey and snippets and so forth, which you can get real productivity. And based on the Amazon experience, if that situation allows, you might consider investing in a specialty application. But you need to have a well-defined context. You really need to have the technical talent or the skills in order to do this. This is not an off-the-street kind of talent that you can get. And you need to somehow minimize the human in the loop there. And if you have all those conditions, then you might have something that really is extreme. And the Amazon experience really was quite remarkable. So there are lots of things that are here. So we continue to play around with this. It's continuing to be a topic of conversation. There's a lot of literature being now. It's very hard to actually keep up with all the literature. So much is being written, but there's a lot of promise here.
Yep. Lots of questions and comments, Mark. So if we could pivot to one of them. Alexander had asked, or comment. The whole exercise seems to be around static code analysis. What about taking into consideration runtime semantics of the code? Otherwise, all these checks are junior level only.
I don't know if I agree with the junior level only check, but he does make a good point. I mean, it's a he, that you can use similar kinds of analysis of runtime behavior as well. I have seen some studies about that. They're not nearly as comprehensive as these. The ones that I have seen are looking basically for aberrant behavior, almost like malware type of behavior. Do I see certain kinds of runtime things happening that shouldn't be happening? That may be sort of the first use case, but the conventional runtime testing, I just haven't seen much data on that.
Sarah asked, let me get back to Sarah's question. I just lost it. Oh, there we go. Sarah asked, do the LLMs require buildable code or look at the broader code context? Or can it work with smaller snippets, functions, classes, files, etc.?
So again, different systems work in different ways. To repeat something that we mentioned earlier, context matters. The more context it has, the better the systems perform. So yes, it can work in snippets, but you're going to wind up getting a lot of comments like, to be very, very somewhat facetious, the variable I isn't initialized. Well, yeah, it's because initialized in the outer context that you just didn't see. So yes, it can. Many of these systems can operate on code that's not complete, code that doesn't compile, and so on. But realize that the kinds of answers you're going to get are going to be relative to the context that the system is seeing.
Nicholas asks, have you investigated or pondered the efficacy of code-to-code translation accuracy using an LLM? For instance, the accuracy LLMs exhibit in turning a Python script into its Java equivalent.
So we mentioned the Amazon experience. I will promote other research that's going on here at the SCI. James Ivers actually is doing work exactly on, not the particular languages that you picked, but on translation, using these kinds of technologies for doing translations of code from
Tying the knot, was that the one?
Pardon me?
Tying the knot, was that the name of
I don't remember. James Ivers is the lead researcher. I just don't remember the name of the project offhand. But it is about using this kind of technology for doing translation of code from one to another. There also is a DARPA project called Tractor, which is trying to convert from C to Rust. But the fact that DARPA is, spending however $100 million that DARPA puts into research projects, sort of gives you an indication of how difficult they perceive that problem to be.
We're down to about a minute. So like I mentioned, we got tons of questions prior to the webcast. Maybe we can do something with these where we get some responses or a blog post if you have time, but I think it's something to be of interest. I'll get these to you. Last question, if we can get it in about a minute. My favorite question was, what's next in the next 5 years? If you got a minute, what's your predictions that we're going to hold you to?
Bullet number 3, you're going to see this being used in very specific contexts that will improve performance in a variety of ways. And it might get much, much better at some of those than it has in some of the others. The auto completions will be better selected. The ability to pull out the documentation and make good suggestions will improve. As I mentioned, amongst the researchers I speak with, there believes to be there's a plateau of just straight models from the training. but there's an awful lot of agentic systems that are being used and where you use things like RAG architectures to extend the technology. So rather than pretending that you're going to build a bigger large language model, bigger generative AI system, you're going to augment it with additional kinds of analyses. And together, those combined systems, those heterogeneous systems, will start producing better results.
Great. Or great discussion today. Thank you for sharing your expertise. We appreciate it. We'd like to thank you all for attending today. Upon exiting, please hit that like button below and share the archive if you found value. You can subscribe to the SEI's YouTube channel by clicking on the SEI seal in the lower right corner of our video window. And our next webcast will be on October 14th. Our topic will be Q-Day Countdown. Are you prepared? With Brett Tucker, Daniel Justice, and Matt Pekovic. Registration information is on our website now and will be emailed out as well. Any questions from today's event, please send to info@sei.cmu.edu. Thanks, everyone. Have a great day.